Yeah, let's recap what we did last week. Yeah, we were discussing functions of several variables. So it is very important to identify the maximal domain of a function and the range as well, right? Range. So this kind of function, the range is all positive numbers with zero. Yeah, on the circle, get zero function value, right? No. So no, range is range for this one is from 0 to 5. Yeah, from 0 to 5. Yeah, so all values from 0 to 5. Yeah. So that is range. Yeah, because of this, if you have negative numbers, if you have number greater than 25, you get negative. So that means square root of a negative number becomes a complex number. We want this function to be real. So we have to avoid that, those negative values coming from x and y. Yep. Okay. This could be from 0 to so this is 4. Yep. This is for the range of this one is 0 to infinity. Yep. All values between 0 and infinity, including 0 as well. Yeah. On the sphere centered at the origin with the radius 4, on the sphere you have 0 function value, and outside of the sphere you have all positive values. Yeah. And come to a map. So that is very important for the next part. Let me check. So if you have a mountain or something like that, this kind of shape, you slice off this, let's say this surface parallel to OX. Let's label this. This is O origin, X and Y. Y. So you chop off this surface parallel to OXY plane. Then you get a set of circles. Set of circles. So here you have different heights. You select different heights, and then you slice off the surface parallel to OXY plane. Then get a set of circles. Then you can draw those circles on this plane, XY plane. If you change the height, you get different circles. So this is called the contour map. This is called contour map. Contour map with point 0. Can you please arrange another time? I will ask others. I will ask do me. Let's see. Maybe I will give another test next week. Let's see. If you miss that, and I will consider that from that test. Let's see. So you get a series when you slice off that surface from different heights parallel to XY plane. Remember, this is the surface. This is a circular surface. You chop off, you slice off this surface from different height. You get different circles. You put those circles together, then you get a contour map like this. So this is called the contour map, right? So these are also called, these are level sets. So you get another. This is one level set. I think this is called level curves. Okay, level curves. Level curves. So this is a level curve, and you get another level curve. If you slice that surface from a different height, and you get different level curves. Yeah. What is the time? 15 minutes. Let's see. Yeah, but let's focus on this lesson today. Yeah, this one is very important. I think I give a problem related to this. Yeah, that's why. Yeah. So this is very important, right? Yeah, let me set the ground for this one. Yeah. Yeah, so if I cut that, if I cut that surface from different heights, you get a circle. If this is a circular or sphere or half of sphere, hemisphere, if you cut this surface from different places, from different heights, get a circles, right? Get a series of circles centered at the origin here. So if you put those circles together like this, this is called contour map. And or you can say this is level curves. Yeah. So you cut the surface from different levels. Yeah. So then you get a level curves like this. If you cut this mountain, let's say this is your mountain, if you the slice of this mountain from different height, you get something like contour map. Yeah. So from remember when you deal with maps and everything, you get, so this is the height of the mountain. At this height, I use slice of the mountain from this height. So then you get this shape, this contour. This is a close level curve, right? Level curve. So when you chop off this mountain from different heights, you get a set of level curves like this, right? I think you see these things when you study not history, what do you call geometry? No, geography. Yeah. Geography, yes, these kind of contour maps. So, level. Okay, right. So that is important. Okay, let me set the stage for this one. So today, so this is the motivation, right? So if you have a mountain like this, right? So, yeah. So, right. Now we are going to discuss directional derivatives, right, of function, of a function of several variables, right? Gradients. We are going to talk about gradient of a function of several variables and directional derivatives, right? So this is the motivation, right? This is the motivation why I'm going to talk about these directional derivatives, right? Yeah, so this is the motivation. Let's say, so we have a hiker, right? So he is interested in hiking this mountain, right? So this is the three-dimensional trial. Yes, this is the three-dimensional path he is taking, right? So he's hiking this mountain along this path, let's say. And if you consider the two-dimensional projection of this path, yeah, this is the two-dimensional projection, and these are the level curves. If you slice of this surface, this mountain from different heights here. So here, so heights are given here. You look at these are the heights. Heights are given, right? This is the corresponding level curve for this height, and this is the corresponding level curve for this height. Right? Height is constant when you consider. So, yeah, for instance, if you consider this level curve, then everywhere height is the same value. What is this value? 800. I don't see the number. I think 800. Yeah. So on this level curve, you get the same height. Okay. All right. So, and this is the OXY projection of his path, and this is the exact path, three-dimensional path he's taking to climb this mountain, right? Okay. So we want to find the speed of this hike in z direction, in z direction. So how do you find the speed? Speed. We need speed of this hiker when this hiker is climbing this mountain. So we want to calculate this speed dz by dt. Yeah. So that is the motivation. We want to compute hiker's vertical speed. So that's the real motivation. So how do you do that? That's why we are talking about directional derivatives, right? Okay, let's consider, okay, this is the surface, this is the equation of the surface or mountain. Z is equal to f of xy, right? And so this is the equation of this mountain. If you know the equation, you can find definitely vertical speed of that hiker. Yeah. Right. So so this is the xy projection of this hiking trail, right? So you can see that, and this is the real three-dimensional path. Yeah. So this is your familiar path R. Let's say vector R depends on T. Yeah. So X component Y and Z. Yeah. And two-dimensional one gives you X of T, comma Y of T, which is this red path. It's taking this red path, right? And this is the projection of OXY plane, OXY plane. Yeah. Okay, so this is the motivation, right? Okay, let's see. Yeah, let's slice off this mountain. Yeah, through this point from different angles. If you slice off this mountain in this direction, through this point, so you get a curve. I don't see this. Give me a second, right? Give me a second. Let me. So I'm going to slice off this mountain through this point. Yeah, different angles. So if you chop off this mountain in this direction through this point, you can chop off this. You can slice off this mountain through this point in this direction, red one, this direction. You can chop off this mountain through this point, always through this point in this direction. Yeah. So you can change the direction, the way you slice off, right? the mountain, right? So if you change the direction, right? So you get different look at the cross section. So if you slice of so this mountain through this point along this direction, you get this curve here. Red one here, right? Then you get so if you can so you get a two-dimensional curve, right? So this is a two-dimensional curve. This is a two-dimensional function, right? So then like y equals f of x, f of x. So if you know this equation, if you know this cross section, you are able to find the slope of this mountain. Slope of this curve, right? Slope of this curve. Or you can find the tangent to this curve at this point, right? So very easy, right? And let's say if you change this direction, you change the direction. Okay, you now chop off or slice off the mountain along this direction, right? So when you slice off, you get this two-dimensional curve through this point. Yeah, so you are able to find, now you get a 2D function like the two-dimensional curve. Cross section is a two-dimensional curve that passes through this point, because we all the time chopping off the mountain through that point. So then you get a different function, two-dimensional function. If you know that function, you are able to find the slope. I differentiate this once, dy by dx is equal to f prime. So you are able to find the slope of the mountain at given point on this curve, on this intersection curve. So very easy to find, right? Okay, this one I slice. So look at this one. You have the mountain. You slice off this mountain parallel to x-axis. So this is your x-axis, and y-axis is this one, and perpendicular one is the z-axis. So now you slice this mountain here. This is the projection here. Through this point. Parallel to x-axis. Okay. So y does not change, because y does not change. Y takes this value here on this on this plane. Y takes this it doesn't change. Y does not change here, but x changes. Then you can so if you want to find the derivative at this point, right? So you have to find the partial derivative of f with respect to x, because y does not change here. Y is a constant, right? If you chop off or if you slice off the mountain through this point parallel to x-axis, y is a constant value, but x changes. So here you get a two-dimensional curve. Y equals x. This is y equals f of x, right? Or g of x. Then how do you find the derivative? How do you find the slope? Just differentiate with respect to x. That's all. So if you have several variable functions like this, this is a function of this mountain. So how do you find the slope? Slope. Yeah, so this is the slope. Uh, yeah, so when you chop off or when you slice off the mountain parallel to x-axis, yeah, y does not change. So then you are able to find the slope. Yeah, with respect to x-axis. Yeah, because x is changing, y does not change here. So that's why you all the time find the partial derivative of f with respect to x. When you find the partial derivative with respect to x, partial derivative of f with respect to x. So y is a constant value here, right? So that depends on, yeah. So you could slice off this mountain from here. Yeah. So then y takes this value, right? And then you are able to find the gradient or slope of the mountain. Yeah, slope of the mountain along x direction, along x direction. So this is the change. Yeah. So this. Yeah. So what is that? The slope of the mountain along x direction through this point is partial of f with respect to x, with respect to x. And if you want to find this slope or tangent to this curve at this point, yeah, you have to substitute that point. So let's say x value, is a. Yep, x value is a. X is equal to a, and y is the y value. Let's say y value is b. Yeah. So when you plug these value into this derivative, you get the tangent to the curve at this point. All right. Does that make sense? Similarly, you can find if you slice off the mountain parallel to y-axis, this is y-axis, right? Then what happened to x variable? X is a constant. X takes this value here. I don't know what is this value, right? X takes this value. Then here you get a curve. Here like this, here you get a curve. Then how do you find the gradient of that, or gradient of this mountain when you move along this y-axis? Yeah, move along this direction. Yeah, you could find just take the partial derivative of f with respect to y. So y is the variable, x does not change, it takes this value here. Don't know what is the value. So I think this makes sense, right? Any questions? Partial of f with respect to y. If you know this value here, let's say this is a, x value is a, and so this gives you the slope of this curve here, two-dimensional curve. Then you slice off this mountain, you get the slope of this curve. So if you want to find the slope at this point, substitute that point. What is the value of that? I will say value of that point, y value at that point is p. Then you get this slope here, the slope. So all right.